This is lecture number 9, and yesterday we started looking charge pump based PLL after looking at the phase and frequency error detection. So let's see where we were. So any questions before that? Yeah. So that positive and negative is with respect to a common mode voltage, right? So if your common mode is ground, then you are looking for positive or negative. If your common mode voltage is VCM, some finite positive value, then you will have variation across around that. So that is not a problem at all. Okay. So yesterday look we had a PFT which gives me up and down signal, and then I used switch current source to convert these pulse width modulated signals to a proportional voltage like error, which is proportion output voltage, which is proportional to the phase and frequency error. So this is, I'm saying, just this is up signal, and this one was down signal. The input is, one input is reference, and the other input is coming from the output of the VCO, which you can call as a F out. We will just write it here. And the output of this charge pump goes, right now I have just used a single capacitor to change the control voltage of the oscillator. And we have seen that we require one additional integrator in the loop previously for the frequency acquisition. So now, so let me just partition this in different way. So whatever you are seeing on this side is a part of the filter. You can call it a filter, loop filter, integrator, and all those things will come on this side. This box itself is charge pump. Okay. And phase frequency detector only gives me error which is pulse width modulated. Okay. So the output of phase frequency detector, which are up and down signals, the pulse width of the up minus down signals represents the what is the error at the input of the PFT. Charge pump converts this error into proportional voltage or current. That voltage or current is filtered, or you can say integrated, by anything which is following it. And once that gets integrated, that goes to a oscillator as a control voltage VC control. So right now in our PLL only these blocks exist. So here the output frequency is F out, the phase is, I can say, phi out, or the signal is, you can say, means out is the signal, and this is a voltage signal. Okay. So now I model whatever we have right now in the loop, the small signal model of this loop. As yesterday we see that the PFD plus charge pump can be modeled with the gain of ICP by 2 pi. This is PFD plus charge pump. So we say this is reference and output signal. Now this thing goes into a capacitor C1. And what is the gain of the VCO and transfer function? K VCO over S, where K VCO is in radian per volt. Okay, so I have V control. Right now this is the only loop. So now I am writing, so all these things is working in terms of voltages and currents, but now we are considering only the phase in those signals. Okay, because PFD is giving you phase error signal, and that phase error is converted by charge pump to control the control voltage, which controls the frequency and phase of the oscillator. So the loop gain which I am writing, or the analysis which I am going to do, will be with respect to the phase. Okay, so now the loop gain of open loop gain, let me make it more clear. The open loop gain of above PLL is ICP uh, by 2 pi, or let's say, to avoid any ambiguity, I will have phi out by phi in open loop is equals to ICP by 2 pi times 1 over SC1 times KVCO over S. Okay. So if I plot the Bode plot for this PLL, which is mod of open loop gain with respect to omega, this is minus 40 dB per decade, right? And the phase, so let me on the same axis just say this is the magnitude of loop gain, and angle of loop gain is always 180 degree. Sorry, this one is minus 180 degree. Everyone gets that, right? There is nothing I'm. Hmm? That is not. No. So, okay, if that's the confusion. So, PFD output is phase error. Input phase error, it gives you the information is still which we are processing is the phase error at the PFD output. That PFD output phase error is means the current proportional to that phase error is pumped, right? And current is pumped into what? An impedance. You get that? So if you want, you say output of this PFD is in units of radians. The charge pump output is, you can say, ampere per radian, right? Ampere per radian into impedance. 1 by SC, you can have an R or something, that will get converted into a voltage, volt per radian. This should be volt per radian or volt. So, yeah, ampere per radian into ampere. If you look at the final output, right, ampere per radian into radian is ampere, ampere into impedance, which is ohms, will be volt. So units are consistent, right? Yeah, charge pump. So, okay, so let me make it more, if that's the confusion. So let's say the PFD output is this, right? I'm just writing at PFD output, right? What do you do with respect to the PFD? So what is the phase error? This is the phase error, right? Now this you basically push in the pump in the current which is proportional to this phase error. Okay, so current proportional to this phase error, you have, that's why this charge pump ICP means, so just Okay, so the charge pump pushes in the current proportional to the phase error. So if you look the whole charge pump means if you look at a current source, that is the units are only ampere, but the current which is pumped into the impedance or loop filter, that is proportional to the phase error. Okay, so that's why that is ampere per radian. No, it should be volt, right? Your phase error is in radian. If you look at phase error is in radian, charge pump is ampere per radian, impedance is in ohms. Means if you treat it as a ohm or if you're treating a reactive impedance, that is a other way. So that is in ohms. So this is equivalent to I into R, which is volt, right? KVCO is radian per volt. This is KVCO unit, right? So final output is still radian. So you got that thing. Okay. This one is a KVCO units. So, or let me just say this is radian per volts here. Okay. Any confusion so far? Okay. So the loop gain, the with only one integrator in with this means with only a capacitor in the loop, you have two integrators in the loop. So it's a type 2 PLL, and the phase is always minus 180 degrees. So what's the problem? Stability is an issue. So here stability is a concern. So this is not stable, you can't use it. So what you can do, you need to add a, no, one interesting thing is you can say that without using any active block here, with ICP and one capacitor, I am able to realize an ideal integrator. Right? Had you done any voltage source, unless you go for an active block, it will be difficult to realize an ideal integrator. Means in terms of voltage source, means integrator realized with the voltage source, you can think of right. This is what you can ideal integrator means. Assuming the gain of the amplifier is infinite, that is an ideal integrator which you can realize. Whereas a charge pump plus one single capacitor gives you the characteristics of a ideal integrator. Okay. So now since stability is a concern, we need to add up a proportional path somehow or add a zero into the zero in the loop to stabilize it. Okay. Now that zero can be easily inserted with a resistor here, R1 if you want to call it. What happens? Let's see. So now with a changed loop filter for stability reasons, earlier I have ICP going to C1. Now this changes to ICP R1 and C1. So this node is still the control voltage node. So what we have is means if you look the out V control of S, that will be ICP. Let me just, since we are writing in Laplace domain, I use uppercase here. ICP times R1 plus 1 over SC1, which is ICP into 1 plus SR1C1 by SC1. So the previous block only had ICP by 1 over SC1. Now you have additional term which is SR1C1, which is a zero you introduced for the stability reasons. Okay, so now the open loop gain of PLL is equals to ICP by 2 pi. Then you have 1 over, sorry, 1 plus SR1C1 by SC1 into KVCO over S, right? Now for this particular loop gain, so let me again do the Bode plot for this omega mod of absolute value of loop gain. So I am still having two poles at 0 and then two poles at frequency equals to 0, and then at omega z, which is your omega z is equals to 1 over r1 c1, and omega p1 equals omega p2 is 0. Okay, so for this the phase of the, so let me, so this wherever the loop gain is crossing the omega, means crossing in dB 0 dB, this is omega. I am just calling this as unity gain frequency. So what you have, you start with a minus 180 degree phase. Now angle of loop gain, starting with minus 180 degree phase, and so this one is minus 180 degree, and this point will be your minus 135 degree, and at a very high frequency you will reach, is there exactly, you can, if you plot it, you can exactly, you can get how, at what point it will reach, but the final point will be minus 90 degree. So you can now, what is the phase margin for this particular loop gain? Can be close to 90 degree. Okay, so this one is a type 2 PLL, which is stable, and it has two integrators. It can have a frequency acquisition, ideally infinite here. Okay, so any questions so far? That all those things depend on your noise characters as far as in this PLL. So we will see what should be the actual location of omega z, right? But that thing will be decided by the noise. Okay. So it depends on what unity gain frequency you want. That is what bandwidth of the PLL you want. It will depend on that, and the phase margin also. But it is easy to achieve a 90 degree phase margin in this one.
Actually, here we had this integrator in unsolved receiver. I mean, just because that is in phase domain, so we need an integrator in voltage domain.
No. So, okay, can you just repeat your question?
Integrator, you know, an integrator is there in receiver. So somebody has to ideally need a separate integrator.
Okay, so the integrator which you are, so your question is, we have one integrator in the loop, why we need the second integrator? It's not, okay, first thing is, it is not regarding the voltage domain of his domain itself. The VCO, which acts with the transfer function of the VCO, which is acting as an integrator, right? That is actually converting the frequency information to the phase information. Okay, but where do you get the frequency information? For that frequency information, if you have means if you just recollect, for the frequency information we need to have one integrator from the, because we need to integrate the phase error to get a certain frequency error information. We started with the type 1 PLL, if you remember, right? And type 1 PLL, the frequency acquisition range of type 1 PLL is limited. Okay, so we needed a one additional integrator in the loop. That time also we were having the VCO. That VCO was just converting the control voltage. See, in case of a VCO, it converts the control voltage to frequency proportionally. But the output phase is an integration of this frequency. So that integration is actually a frequency to phase conversion. Okay, the additional integrator which we put to get the frequency error information, means you not to get the frequency error information, I would say to get a certain control voltage which is proportional to the frequency error information. And we have seen this thing, that means I have just introduced the proportional path right now from the stability point of view, right? But we have seen in the type 2 acquisition PLL, if you do not have a proportional path, you actually do not develop the control voltage itself to begin with. So you need to have that asymmetric beat node in the system to develop a certain, and to start developing a certain DC voltage which you integrate. So it's two different ways of looking at it, but it's doing the same thing. So does that answer your question, that VCO as an integrator is something separate? Okay, and an additional integrator you need means if I do not want to have any frequency error information, if I say the frequencies are the same, I just need a phase log, I will not go for this integrator at all. Okay. Yeah, any questions? So far you have seen that I started with the one integrator, and then I added a proportional path for the stability reasons, and I am getting a good phase margin. It's a stable system, so I should be happy, and it's all done. And this is the PLL design, right? You get the frequency, you get the phase error. Okay, but things actually start after this in more complicated manner, that we have, you see that we have used a PFD, which is switching your charge pump switches as such to pump in the current or take the current out of the filter. Now you see, now as soon as I have changed one single capacitor to an RNC, I started calling it a filter. Okay, means I am not calling it as a real integrator, ideal integrator as such. So there is no as such distinction between, oh, like one was an integrator, next was a filter, means all are the same. It's just what I call them at a point. So let's see what the problem with the PFT is, which will introduce additional things to this filter. So PFT output, if we have seen for a, so let's say this is your R and this one is your V signal. Okay, now the up signal is this, and ideally down signal is this. Does everyone agree with this? Because this is what we have started with actually, up minus down. Now if I say this up is actually not this but only this, so your down signal will be here like this one, right? Now this up and down signals are used for switching the current source, because there is no ideal switches. You are using some transistor to switch the current source. It's too bad. So don't need anything here. So this is ICP. So because I am using a PMOS, I will write it here as up bar in place of up. It's a inverted logic, and this is still down bar. Okay. So can you comment if the time width of the pulse width of the up signal reduces, what is the consequence? it may not be able to switch on. So now, as you say, so initial means when we started this PFD, we had a nice gain characteristics passing through 0. So this is a V of up minus down bar signal. This is with respect to phase error and 2 pi and minus 2 pi. Okay, this is the ideal PFD characteristics. Now what you are saying is, if my phase error is very small, where my switch will not be able to switch on itself, right? So what my output is 0. Okay, that means somewhere near 0, I will have my output is 0. So in place of the ideal characteristics, now I started having something kind of this. Because of the real characteristics of the PFT phase frequency detector. And this region is called as dead zone. Because your feedback loop is broken, because if the phase error is within that range, you will not be able to correct for that phase error itself. Phase error. So you will keep on accumulating the phase error till the time you jump to a value which is higher and your switches can switch on. So this dead zone will actually lead to you more jitter, tethering jitter. Okay. So what can we do to suppress the bad parts of the dead zone? We can keep on using a much finer and finer technology such that the dead zone will keep on reducing and reducing. So maybe from 100 picoseconds we can come down to 10 picoseconds, but we are still 10 picoseconds. Okay. So you cannot complete, means you can suppress with the technology, you can reduce the width of the dead zone, but you cannot completely eliminate it with this implementation. Okay. So one thing is suppression, or another thing is you try to eliminate it completely. So what is the way to eliminate it? So let me say, to a starting point is that minimum T on time for PMOS and NMOS switches to switch on. Okay. Whichever technology you use, there will be some minimum T on time which is required. Okay. So now, can you tell me that how can I use this information such that I do not land up in this dead zone kind of characteristics. So if I assure you that no matter what the phase error is, the up and down pulses will always be the minimum width for which up and down will be high will always be T on. That is the minimum, right? Then you can say if the minimum time is it, then my switch will always switch on. Okay. So let me just say. So you have seen this red one which I have plotted here as a very less phase error for which it cannot switch on. So I add up, let's say T on period to this, so that I can switch on. Now if I add a minimum T on period to, so let me just say this is T on. If I add a minimum T on to this and I do not do anything to the down pulse, then you are actually putting more deliberately more error information. What can I do? I can add the same T on to this also. Now for the time, when both of them are on, means even both PMOS and NMOS are active, right? There is no current going through this path. Okay, so everyone get that thing. So what we do is, let me just plot this part again. I have R and V signals. So this I am plotting it is in a bit exaggerated picture where you see that the phase difference which I am plotting is a significant part of the pulse, but I can have this as T on period. So this is up and down pulse is this, same as T on. Now there is no problem as such, ideally. Okay. So even if my actual phase error, which is this part, even if this reduces to 0, right, both an up and down pulse will get activated, and ideally they will pump in a 0 current into the filter. So no issues, right? Sorry. And the way you can do this thing is for a PFT. We can just look at the. So we had this D flip flop, which we use for the up. So we have R, V, output is down. What we were doing initially was we were resetting both up and down. When both of them go high, we were resetting this with respect to, this is what we were doing before, right? Now in this particular block, what can you say to delay the reset for both? So look at here. As soon as your V pulse comes, right? Earlier we were resetting at the very instant in an ideal fashion. Now I want to delay the reset. What can I do? Means this is nothing but effectively an increased reset period. Sorry, not the reset period, increased delay for the reset to get activated. So that can be done by just adding a delay in this path. Okay. Now, what will be the conceivable, like that part when you add a delay? I think that would be a good assignment problem. As such, you can see what happens because of the reset. But this will surely uh, give you the characteristics here, linear crossing to 0. So this one is PFD with finite T on. Okay. So now we have a PFD which is having a finite T on period. So see now how my control voltage changes. So again, I will keep on doing, plotting the same reference and the other one. So I have a reference, and let's say this is an out pulse. This is an actual phase error. In response to this, I have my up pulse, which is here, plus and the down pulse is this. Okay. Now, and now you see that I am using this PFD with a The filter is now not anymore only C, the filter is R1 C1 ICP. So now I want to plot V control. What happens to V control? Okay. So let's say if this is 0 and the output I don't know, what will happen as soon as the rising edge of the up comes? So this jumps to ICP-R1, then it integrates, then ideally it comes down, okay, and then it remains flat for the next cycle. Okay, so this is the case when I am showing you with a finite error and there is no as such difference. There is no as such difference between the top and bottom current source. Means that so this is particularly with the case when I am having switch up and down. So this is, let me call this as I up and I down. So what I have shown you, the V control characteristics are for I up and down, when I up and I down are both equal. Okay. Now let's say the phase error becomes close to 0 or very less. What will happen if I up and I down are not the same? So charge and discharge is like you will have some, means now whether I up is greater or I down is greater, you may have a different slope here or here, whichever way, depending on which is greater, I up or I down. So this one will be when this one will be the case when I up is not equals to I down. And in any real scenario, you can have an accuracy, but you can never have a infinite accuracy between I up and I down. So some charge will always be. So now, if you see, previously when we had only one single capacitor, we were having a smooth going from 0 like this, right? Now we started having jumps, which is an additional, for any phase error, phase offset or any delta phi, we are starting having this every reference period as such, right? And this is means this can be delta ICP difference between this ICP, this jump can be due to the difference in the current also in a locked state. It can be due to a certain phase offset, right? But this is going to happen in the PLL at every reference period. So what we are doing is we are modulating V control. So let me just say we are actually let's call something, and this is ICP dash or something. In addition to the proper any other phase, in addition to the V control change due to a ideal integrator, which is this, we have now periodic current injection into the loop filter. So this periodic injection into the loop filter will cause periodic change in the control voltage, which will then get modulated to the output frequency. Output frequency means this is Tref, right? So these pulses then lead to U F naught plus minus n times F ref modulations. Okay. Means you can always say the F out is KVCO times V control, right? If I am changing V control, just for an example, if I say KVCO times V control is something as A naught times, now write the Fourier series of this to find what harmonics and what values they are. So let me just say, now V control has some Vn sine of n omega ref times t. Okay, this I am writing. Oh, this is not the exact mathematical calculation because this is not a proper square, like 50% duty cycle square wave. You can always find the coefficient another. The only thing which I am trying to show is that your V control is modulated with the current pulses every reference period, and that V control will get translated to the output frequency, and you will have these harmonics now. Okay, so now so far you will have, now if I just want to plot the reference harmonics which or V control has your FREF, 3FREF or 2FREF depending on implementation. You will have, okay, let's just write this as F. You will have some tones in the system. So this is, let's say, V control. Which is actually not good as such because you are getting unwanted tones at the output. Again, how much can you tolerate? That depends on application. And so, since I am talking of the reference, I can say these things are commonly referred as reference spur. Okay, which is defined in mostly in terms of uh, minus dBc per hertz, or sorry, not minus dB. It's defined in terms of units as minus dBc, which is, so let's say if this is my F, if this is my final V out mod, and I have my F out tone here. Okay. Now, if because of this reference things, I have plus minus F out. So let's say this is F carrier. This is F carrier plus F ref, and this one is F carrier minus F ref. Okay. So reference spurs are normally quantified at how many dB C with respect to the carrier. So if this is 0 dB, this one can be, let's say, minus 40 dB C, which means the reference spur is 1/100th of the carrier tone. Okay, these are the units which is okay. So now coming back to the question, now we are having reference spur and we need to control it. We cannot just let it go as such. Okay. So how can we control the reference spur as such? So let me then again ask the question that we are having, we are injecting an ICP into R1 and C1. So there is some net impedance of R1 and C1, right? If I can introduce another impedance at this particular node, which is much lesser than the impedance of R1 plus 1 by SC1, then most of the current will go into that node. It's a parallel thing, right? In a parallel impedance case, so what I am saying to you here is, if I can have some impedance here, let's say Z, which is having a much lower value at the reference frequency at which the current is being injected into the V control node, then I can reduce the spur. I mean, this is just one way of telling it. Okay, and the easiest way of introducing impedance means we do not want to change any DC voltages here also. The easiest way is replace this with another capacitor. Okay. So what we want from here, we want that 1 over omega. So here I am writing it with some approximation. So you can say what we want ideally here is mod of 1 by omega ref times C2 should be much lesser than mod of R1 plus 1 over j omega ref times C1. Okay. That makes sense, right? So, okay, let me ask this. So, if I am having this equation as such, what can you say the C2 should be, higher or lower? I want this actually. Omega ref is a reference frequency. What it should be? Huh? Higher. So, in order to suppress, so higher, so okay, let me say reference is per magnitude, means this is still qualitatively, I haven't gone to in quantitative manner, reduces. This requires that I should increase C2. Okay. But if I increase C2, what other thing can happen? Pole moves in, right? If pole moves in, if somehow, let me say, if the, so the thing is, so far we have this picture for the Bode plot, right? If my pole moves in here, then I have no use, right? So we have here a contradictory requirement. So stability requires C2 should be lower. Okay. So now, if both are having both the two requirements are having a contradictory, let's say it's two things like references per magnitude and stability has contradictory C2 requirements, so there should be some optimum value. Okay. So now our loop filter has actually changed from an integrator first to proportional path plus an integrator, and now this has changed to C1, R1 and C2. Now C2 actually has other effects on the other noise sources suppression also, but that is the later we will look at it. So this is the change loop filter now what we have. Now the impedance of this loop filter is R1 or let me just write it 1 plus SR1 C1 by SC1 in parallel with 1 by SC2. Okay, which is 1 plus SR1 C1 by SC2 plus SC1 plus S square R1 C1 C2. So I will have SC1 plus C2 1 plus S R1 C1 by 1 plus S C1 C2 by C1 plus C2. Okay, so now I will just take R1 as a out. So what I have is S plus 1 over R1 C1, S plus 1 over R1 C1 C2 by C1 plus C2. Okay, and then what is the component which remains here? I take R1 C1 out, 1 by SC2. Is that right? So I just took R1 C1 out, that cancels. Yeah. Okay. So here means to begin, I have omega z as means it will turn out will be omega z R1 and C1, and omega we know from the integrator for the loop means for the whole loop I have omega p1 and this is one pole s equals to 0, one is through kvc over s, this one is 0, and omega p3 is r1 c1 c2 by c1 plus c2. Okay, so now you see very well that omega z is before omega p3. Okay, but it should not be before omega u also, otherwise you do not have the stability. Okay, so let's stop here, and next tomorrow's class we will see how to design an optimum PLL with this kind of loop filter. So let's stop.